Hi, my name is David Bennett. I'm an astrophysicist at the NASA Goddard Space Flight Center. Today, we're going to discuss how we can find planets thousands of light years from Earth using a method called gravitational microlensing, which is a form of gravitational lensing.
We really need to understand planets and planetary systems in the biggest, most comprehensive way, how they're distributed throughout our galaxy, even possibly other galaxies. And microlensing is actually the best technique for doing this.
It's a new way of finding planets orbiting stars. In fact, we monitor about 50 million stars every night, hourly. 50 million stars, that's quite a few.
In '93 was the first microlensing event discovered. And most people who were not in microlensing collaborations just thought the idea was nuts. But it's happening in 1 in a million stars.
So if you have two stars lined up, the foreground star brightens up the light from the background star. It acts like a magnifying glass. And Einstein was the man who predicted this. Yeah, he said that light is bent by the gravitational field, and the foreground star has a gravitational field, and that bends the light as it's passing by, and so in fact it acts as a lens and it magnifies the light. And then we use this to actually find planets orbiting the lens star, because if there is a planet orbiting that foreground star, it'll act as a sort of an imperfection in the lens. And instead of getting a perfect image, we get a slightly distorted image. And we look for those distortions.
Hi, I'm Virginie Battista, a researcher at the Institute of Astrophysics in Paris. I'm going to present a way to discover planets outside of our solar system, thousands of light years away from us, with a technique called microlensing, which is a form of gravitational lensing. Gravitational lensing is a physical phenomenon that occurs when a massive body bends the light rays coming from a source with respect to the observer. It is natural then to call this massive object that bends the light a gravitational lens. If it is composed of compact bodies, such as stars, planets, or even black holes, then we call it microlensing instead of lensing.
We're all familiar with the lens of an ordinary magnifying glass. It's relatively flat in the center, but more curved near the edge. As a result, a light ray that passes near the edge gets bent by a larger angle than one that passes near the center. This design allows a magnifying glass to focus light from a distant source to a point, known as a focal point. This pseudo-gravitational lens is designed to have the same light bending effect as a real gravitational lens with a mass at the center. It's relatively flat near the edge, but curved near the center, because the closer a light ray passes to the mass, the larger the bending angle. As a result, the gravitational lens focuses some of the light for an observer at any distance directly behind the lens. To simulate the gravitational microlensing effect of a planet orbiting a star, we add a second lens. This second lens is less curved to represent a lower mass object like a planet. The first lens has a sharper curve to represent the gravitational field of a star. This model demonstrates the gravitational microlensing method. The lenses we use to simulate the light bending effect of a massive object like a star or a planet are mounted on this stand. The lenses distort and magnify images of a background star represented by this marble. Because both the lens system and background star orbit through our galaxy, the background star appears to move with respect to the lens system. To simulate this motion, we roll the marble on this track. To see a microlensing event, we have to be lucky enough to have our telescope almost perfectly aligned with the source and the lens. In this setup, the video camera represents a telescope, like the MOA telescope that we use to observe the changing magnification. Two lenses can be mounted back to back to simulate a binary lens system, which is a system with two lens masses, such as two stars or a star and a planet. By adjusting the lens positions on our stand, we can model different planetary orbits. Here we show a video of the moving ball shot through our pseudo-gravitational lens. On the right, we have enhanced the contrast to better simulate gravitational lensing, where only the distorted lensed images are visible. In this case, we've chosen perfect alignment between the source track, the lens, and the observer. When the source reaches perfect alignment, the two images merge into a highly magnified ring image known as the Einstein ring. When the alignment isn't perfect, we still get two bright images near the location of the Einstein ring. A binary lens produces either 3 or 5 images. At low magnification, there's one bright image near the source star and 2 faint images near the lens masses. But with a binary lens, the number of images can change. 2 new images can be created. This often results in a large increase in total brightness. In this case, the alignment between the source and lens star is not so good, so there was low magnification due to the star. But one of the images passes close to the lower mass planet, which results in 4 bright images surrounding the planet. Thus far, we've shown what gravitational lensing by stars and planets looks like. But in realistic cases, the separation of the images is so small that it can't be observed by any telescope, including the Hubble and Webb space telescopes. Instead, we see these images blurred together. We call this microlensing, and we are able to determine the exact lensing configuration by studying how the total brightness changes with time. Our international team of astronomers has discovered the first circumbinary planet using gravitational microlensing. Very detailed observations from a network of 8 telescopes spanning the globe allowed us to determine the mass of this system. Here is the light curve of this remarkable microlensing event, showing how the magnification changes with time. It reached a peak magnification of nearly 700, but the low magnification portion of the light curve is also important. Telescopes in Chile and New Zealand measured a long-term asymmetry in the light curve due to the orbital motion of the Earth. There were also subtle differences in the light curve peak, seen from different observatories. Northern Hemisphere telescopes in California and Hawaii saw slightly different light curve shapes than their Southern Hemisphere counterparts in Chile and New Zealand. Observations with the Hubble Space Telescope indicated that this system was not bright enough to be dominated by a single star of this mass. The precise measurement of both these effects revealed that the star and planetary lens system was 70% as massive as the Sun. But the Hubble observations matched the circumbinary planet model because 2 stars of 30 and 40% of a solar mass are fainter than 1 star of 70% of a solar mass. These stars have lower masses than any known circumbinary planet host stars, and our newly discovered planet, Ogle 2007 Bulge 349 LABC, has a wider orbit than any known circumbinary planet. This provides just a hint of the prospects that the microlensing method holds in finding types of planets that are undetectable by other methods.